mechanism to build embedded systems such as the quadcopters you just heard about using embedded DSLs. So at this point I'll hand it over to Pat to let you know what they've been working on.
Thank you. This is an experience report on building these embedded systems with embedded DSLs. My co-authors on this were Lee Pike, who's attending today, Trevor Elliott and James Beelman, who couldn't make it, and John Launchbury, who was with us at Galwa and now has taken a leave to go to DARPA for a bit. He's here as well today. So first thing I want to do is thank Kathleen once again. This work was supported by her program at DARPA, and we also had partners at Rockwell Collins, University of Minnesota, NICTA, and Boeing on this work. And mostly I want to thank Kathleen for her guidance on this project, making all of our stuff available open source. This is valuable to us, it's valuable to hopefully others in this room and in the community. We had a goal in this program of building a high assurance helicopter controller. This is Boeing's model, which Kathleen talked about. It doesn't really fit near my desk. So instead, I went down to the mall and I got a toy quadcopter. And this is just like we saw in that video in the last talk, an AR drone. And we've replaced the electronics on it with some open source electronics. So the challenges on building this, that it's a embedded system, it's a microcontroller. So it's a very small computer with limited resources. The system has to be hard real time, which means there's a fixed deadline between when you get a new sensor sample in and when you have to send new control outputs to the motors. That's about 1 millisecond or sometimes even less for some sub-deadlines in there. And the system has to be safe. There shouldn't be any bad behaviors, bad states you can get in. There shouldn't be any bugs, effectively, and secure. Of course, we had a red team, a penetration testing team, checking our work. We knew that from the beginning, so that kind of helped us not just be able to say it's secure, but to know that we'll have to show somebody who's going to be looking very hard to prove otherwise. So that's actually a very valuable thing when you're in your engineering process on this kind of system. Our other constraints were that we only had about 3 engineers and 18 months to do this body of work. And that was to start from scratch on the system, effectively. And I know from other projects, there's a similar open source project that are just written in C, that you're looking at somewhere along the lines of 50,000 lines of code. So not a small program, not a huge program, but significant, especially for all 50,000 lines of those to effectively not have any bugs. So I'll talk a little bit about what makes embedded systems, this problem domain, pretty challenging. There's billions of these in the world, billions sold every year. Like Kathleen said, they're from everything from industrial control systems that run power plants and sewage plants. They run airplanes, they run appliances in your home, your car, everything. So there's a lot of software being produced for these. And they're basically just really old computers. They don't have memory management, they don't have hard disks, they just have a little bit of RAM, a little bit of ROM. They are very, very small and very, very cheap. So this is which is the 1 penny cost sensitivity is huge in this market. That if you can fit something into a smaller pin count, then you do. And of course, with your computers from the 80s, you get the development tools of the 80s. So none of the nice work that's been done by folks in this room and others over the last 20 odd years. You basically just get C. Those are your choices. So if you build all your programs in C and they run on a system without any built-in hardware protection, you get all the security flaws you expect. These are buffer overflows, stack overflows, stuff that wouldn't surprise anyone. But it makes it a lot harder when you can't push a patch. A lot of these aren't connected to the internet, or if they are, they might not have that kind of the certification environment or other constraints prevent you from doing that. And again, as they're more interconnected, they're connected to your phone, to the internet, to each other. There's more attack surfaces for a hacker than ever. There's more motivation for a hacker than ever as they become in control of more and more important things. Kathleen already told you a little bit about the University of Washington and UCSD's work on the car hacking bit. These were all basic buffer overflows, and we thought we should be able to do better than that. What languages, what technologies did we have to consider in our approach? Of course, we would have loved to use Haskell or OCaml or one of those languages. It's not really suitable for this system because it's a very, very constrained bit of hardware. And certain things like garbage collection can be incompatible with hard real time, meaning that 1 millisecond or even microsecond deadline doesn't help if you pause to collect GC. So the industry basically just uses C or sometimes C++. And when they use C++, they can often only use a subset of the features of that language. And the big problem there is that you're in a constant trade-off between safety and productivity. The Jet Propulsion Lab, NASA, they write some very, very high assurance C that runs on satellites and Mars rovers. It's extremely costly because they have to put in a lot of both technical and human processes throughout that development cycle. So you trade off a ton of developer productivity in order to get that safety in the existing tools. So we got to build our own tools in this program. And that's where we got this experience report from, that we were able to start with this completely clean slate and say we're going to write all of our code in a new language wherever possible. We're able to design a language that does all of these memory safety and buffer overflow properties completely safe by construction, correct by construction, so that we can eliminate large classes of bugs and never have to worry about those again. So we designed and built a DSL compiler, and having experience doing this before, it took us about 2 or 3 months from when we first started writing the language to when we had useful hello world code. An embedded system that would be blinking an LED is typically your hello world. So we were able to do that in just a few months. As we said before, the language is called Ivory. It's embedded in Haskell. It uses some of the newer features of GHC, so it works on 7.6 and 7.8. And it compiles down to C, because we didn't want to have to write our own cross-compiler to these embedded platforms. And we said that we could build on other work there, like CompCert, for having a trusted chain there. So as before, this is a safe subset of C embedded pretty straightforwardly in Haskell. And the most important things was that we got memory safety, type safety, and that we could get rid of a lot of the implementation-defined and undefined behaviors, which plague C programmers. So there's a lot of integer behaviors and pointer behaviors that we wanted to completely, eliminate from being exposed to the user. And the other thing was, in this embedded system space, because you have a lot of trouble, you want the programs to be deterministic, you don't have very much RAM, there's very often no heap in these systems. So we decided that there would be no heap in the Ivory language. You would only be able to allocate global variables, like global C variables, and variables on the stack, which is the simplest heap. Like I said, we embedded it in Haskell because the Haskell type system is strong enough that we can do all of the domain-specific type checking in the Haskell type system. So all of our memory safety properties about allocation and type safety is all checked by the Haskell type systems. We didn't have to write our own type checker. And that saved us a lot of time in the development process and made it very productive to use. And of course, the biggest thing that made it productive to use is that Haskell, just ordinary Haskell terms, are the macro language for Ivory. So it's very easy for a Haskell programmer to pick up Ivory and start writing macros that are, all the macros must be safe, and then the programs constructed with them must be safe. So there was not much very exotic about the way we built Ivory, and I'm not going to go very deep into the design decisions we made there to focus mostly on the experience here. We just use a simple monad embedding, and the AST under the hood is pretty printed to C using the language C quote package. Just a little bit about the syntax. We'll just follow the types through one example to show you what kind of things we embedded in the type system. So we'll define a function addArray, and that's a def. Def is a procedure type in Ivory, and it takes a single argument or 2 arguments. One that's a reference to some global array. A reference means it's a mutable thing. And just another int 16. So the array is of 10 int 16s. And then we take a second int 16 as an argument, and it returns void, effectively. And then we make that procedure by giving it a C name as a string, and then just using simple lambdas and reference value body creates the scope for the function body. And then I'll define the actual body. And that's just an ordinary Haskell function that gives you an expression in the Ivory monad. So that's the basic form of these expression or statements. And one of the things we did was make a map combinator, an array map, So what that's doing is inferring from the length of the array 10 up there, exactly the bounds of the array, and it's going to give us an index into that array for every element, and then we're going to store the value given as a second argument into the array. So this is just setting an array to all the elements in it to a constant. It's a very simple function, but that's just one of the things we're able to do because we have the type inference that you couldn't do in C. To talk about how we compose those, that was a simple procedure, and we composed those plus global memory areas into modules, and those just emit a C header and a C source file. So just like in C, we're composing programs that essentially all the names are strings. There's a global namespace, and the user is responsible for managing which names end up in which files. And there's some public-private stuff, so you can expose certain names in the headers or not. But that's not very complicated. But the composing it is basically just like the way you do C programs. It's a very similar model, and that can be a little cumbersome in programming. But we found that there are ways around it, and I'll talk about that now. We made the Tower DSL as kind of a way of organizing, rather than just procedures, organizing an entire application from the program. And the initial problem we had there was we needed to connect all these different program components into threads and pass messages between them. So we wanted to code generate the low-level operating system primitives, which are often untyped or complicated to use because they're just locking and unlocking. So we wanted to be able to code generate all of that away, and we were able to implement this all as a Haskell macro that we describing in Haskell syntax the system, generate both on one hand a collection of Ivory modules, Ivory code, and then also a system description. And we use that to export to those other tools Kathleen talked about that Rockwell Collins designed into the AADL language. So like I said, the idea here is that we compose these procedures into applications using this DSL built on top of Ivory, where we could just talk about code and state more declaratively, and we collect those into a task, and then we have connections between them. This is just like a basic graph functionality to connect between the tasks, and it makes the user that they don't have to maintain all those background modules of deciding what gets put into each file. That because they're just giving us the bodies of the code and what the variable type might be, then we can collect all of that into C and H files in the background, and that kind of lifted the layer of abstraction that the user was dealing with. So it became, in addition to just declaring these threads and the channels between them, this became kind of our macro language for describing software components. And one of the challenges there was that every component kind of also had a scheduler assumed with it, and that's one of the challenges we're working on now, is kind of decoupling those two so we can both talk about software components and talk about schedulable units and have those be separate ideas. So to talk a little bit about the way we built the quadcopter, we were given 18 months to do this system from the ground up. We did have some existing open source code that we used as stepping stones along the way, and at the 18-month mark there was still a little bit of that code left in, but we've now we're almost at the point where we've completely eliminated it and the whole system is written in Ivory. So to talk about how much Ivory code we ended up writing, the bulk of your engineering in these low-level embedded systems is in the drivers. You get this chip, you get a document from the manufacturer describing the low-level register level of the chip, and that's it. Everything else you have to build yourself. I mean, you can use existing libraries when you're in C, but there are none in Ivory, of course. So building those drivers was the initial, really big effort. For our first set of code, that was about 10,000 lines. As we've expanded hardware, that's expanding, basically linearly with all the hardware devices we support, whereas the application code stays about the same. The application to fly the quadcopter, we didn't implement all of the full features you would expect on the AR drone, like Wi-Fi control and a camera, but the basics of just stabilizing and flying a quadcopter around only took us about 3,000 lines of code. And that's not radically different from C, but it is different in that we know that it's safer. And the third thing that we had to do was interoperate with an existing message marshalling library called Mavlink. And there was already an existing code generator that was a Python program that took some obscure XML format and output some really gnarly C. And it was one of those things where we didn't want to try to understand the formal specification of how that protocol worked. So instead what I did was I just mangled the Python program that outputs C until it output Haskell files that described an Ivory packer and unpacker. And then I let the Haskell type system check to make sure that was correct. So I didn't have to trust the program that was generating that stage of the code, that XML to Python thing that's very complicated, and I didn't have to trust it for safety of the protocol, that the Ivory type system would check to make sure that I'm not doing any invalid operations there. And then altogether that generated about 48,000 lines of C, which was about on par with what we would expect for a system of this complexity. So while it's only about a 2x improvement, and we have various opinions on how effective lines of code is at productivity measurement, it is an accomplishment to say that those 48,000 lines of code don't have any buffer overflows, don't have any undefined behaviors, and of course that they're sprinkled with assertions that we can test in development and we would hope to discharge with a model checker later. So that was a huge productivity gain, and that we didn't have to verify the code afterwards, that's a large amount of code that's correct by construction. And when we make one little change in the driver that might affect half those lines of code, we still have that same confidence. So as Kathleen said, we delivered this code to the red team for evaluation. And we were able to get a report back that they weren't able to find any of those buffer overflows, those undefined behaviors, that we were able to write application level code that could do a denial of service, prevent a denial of service attack, or detect it when it was happening. I mean, the nice thing was that they didn't find any of those low-level bugs. After about 5 months with the code, they did give us 1 or 2 architecture-level bugs, where it was, the broad system property, because of a way that we didn't think of a case, they were able to think of that case and tell us something about it. So that's something we couldn't get with a language approach. But the nice thing about this is that we don't have to worry about the low-level stuff anymore, so we can just focus on developing those system-level concerns. So we've really lifted the layer of abstraction that we're dealing with. So in conclusion, this was a large application, complex, and we built it pretty rapidly. That we didn't end up with any of those bugs that are prevalent in all the existing embedded systems. By embedding all of the features that we wanted for Ivory safety in the Haskell type system, we're able to check all the safety of our macros and the code that we're emitting very quickly. And that made a fast development cycle, and we could focus on the more important things than C buffer overflows, because we knew that if it type checked, that all that stuff is basically correct. It was the fact that it was an embedded DSL in Haskell that we had this powerful macro system. We were able to build Tower. The first version of that took just about a week to build. And of course it's gotten more complicated from there. And then all just the basic little macros that a user would want to use on a per module basis. Prevent a lot of code duplication and do far better than you ever would do with the C preprocessor, for example. So that allowed us to build compositional programs, and even though these aren't really Haskell, they don't have the same kind of operational behaviors as Haskell programs. It made programming in it feel just like writing Haskell programs. So thank you. We have all of the source code for this project and some documentation on ivorylang.org and MACCMPilot.org. And look forward to your questions.
Use the mic, please.
I understand you're targeting some sort of ARM core in this helicopter. Now, of course, the OCaml native code generator already generates ARM code directly. And I just wondered what are the features of OCaml that your thing is a significant improvement on what could have been done using existing technology?
So one of the concerns we had is that across the embedded systems world, they use a whole lot of different kinds of low-level 8-bit, 16-bit, 32-bit processors. And there's, it'd be very hard to get the code backends for all of those. But there are existing cross-compilers from various vendors. So that was kind of a program, a specific concern that we wanted this to be usable in industry where it might be an obscure, Fujitsu 16-bit that's used in the automotive world. So that was not a problem with the existing OCaml stuff. but just a different concern we had.
Okay, thank you. That was a very nice presentation. So you talked about that you had a restricted amount of memory on these platforms that you were targeting. I was wondering if you had problems with running out of memory and how you communicated the memory usage of a program to the programmer.
So we don't actually have a facility for, we do have a way to collect, the amount of global memory that you use in a program. That's just a basic C compilation. The linker can tell you. We don't yet have a way to analyze the maximum stack depth that you use. We do have, down in the operating system level, a way that, once you've exceeded your stack, it halts in a certain way that you can attach a debugger and find out some information. That's a program we hope to, in the future, using static analysis tools of the C program to be able to find out your maximum stack depth. Or you often have to use, actually, a static analysis of the machine code to figure out how the compiler laid out those stacks. So that's a difficult problem, and we haven't built up that tooling yet, but we think it's solvable. It's just, it's on a per architecture basis you would have to solve it.
Okay. Next question for Oleg. Question is, if you could just state your name and your institution before it'll help the scribes actually take a record of the questions as well. Oleg, please.
Yeah, okay, so I have actually two questions. So one of them, I think that your claim that you generate correct by construction C code. I think it needs to be qualified that you generate correct by construction subset of C code.
Yeah, that's correct.
So because I'm not sure how you would generate, if you allow point arithmetic, how actually you're going to type system assures the safety of it, right? So you probably can claim that in most of the control code you never need to do any point arithmetic, right?
Yes, exactly. We don't do any pointer arithmetic that would be undefined. We just do array offsets and stuff like that. Okay,
and then also somehow, how do you guarantee that the loops indexes within the bounds of the arrays?
So that's defined by, so that's taken care of in the Haskell type system.
But how do you actually, your arrays is statically known? Or?
Yes, all arrays are of a statically known length. That's an important part of that proof.
Okay. And my actually main question is, yes, we all know the advantages of DSL, that it's of course embedded DSL, and it's very easy to get off the ground. But there are some problems, for example, with error messages, right?
Oh, absolutely. So the big problem with error messages in this is that you have to both be, an embedded systems programmer, a Haskell programmer, and for certain things that if you put the wrong number of arguments, you might get a kind error. You have to know the way in which we implemented the Ivory language. You have to go into the source there and look at the type family and the way that so to understand those error messages can be quite difficult, and that's a significant thing we'd love to improve upon.
Alexei Romanov, Huawei Research. Right. I just wanted to ask, you say that you don't allow any undefined behavior, but how do you don't allow signed integer overflow? It seems like you need more complicated type system.
Right. So we can't stop that at the type level, and for all the properties that we can't stop at the type level, we discharge assertions into the C code. So when you're developing and testing, you can have those assertions live, and you can even leave them live in production, I guess, if you like. Depends on your philosophy. But we're hoping to use tools like FramSC and others to analyze those assertions statically and solve them where possible. And the user can add annotations, assert in the Ivory language is just a statement to hopefully help solve those. And that's something we haven't done. I mean, we've done basic work on that, but there's still, of our 2,600 assertions in the Ivory code, a lot of those can't be solved by the tools that we've run on it so far, like FramSC and CBNC.
Thank you.
We have time just for two brief questions.
My name is Kian Okabe at MetaCity Design. My question is how about ATS language or Rust language? They have linear type for memory management. Then without GC, and also ATS language without any runtime, and also can run on 8-bit architecture.
Yes.
Yeah. How about?
think I'm a tremendous fan of Rust. When we started this project 2 years ago, Rust was still in its infancy. I think one of the differences I can tell you we are from Rust is, as embedded DSL, you have a very different approach to your macro system, and all of the macros are typed because they're in Haskell.
No, I think Haskell type is not good for DSL, but DSLs do not have type, I think. Okay? DSLs type. Okay.
Yeah, sorry. Maybe we can talk about that more offline. I'll
Yeah,
try to understand that better.
Well, a very brief question from John. I can't turn it down.
Okay, John Hughes, challenge from Cubic. You retargeted a Python code generator to generate checkable Haskell instead of C. I'm sure that didn't work first time. So I'm curious how many bugs you found by doing that, and how many of those you introduced yourself in the retargeting. How many were there in the original Python?
So I can't say for sure I found any in the original Python, because I took a very let's delete it and start over again approach to the actual pretty printing of C versus Haskell. But we certainly throughout that process, having Haskell check the types of the output is tremendously helpful. But I'm not sure I have a great answer for that.
Thank Pat again for a great talk.